All right, we are recording, so let me hand the floor over to group 5 and let them share with us their design.
Hello, everyone. Thank you for joining today. Welcome to Group 5's presentation of our heliostat, the Lagarto ray. Our group is comprised of Alexander Hong, Matthew Petrick, Gabriel Guanche, Kathleen Anderson, myself, James Sanchez, Christina Brooks, and Ben Lehman. Our presentation will begin with a discussion of our hedgehog concept, then product overview, subsystem analyses, cost, and finally conclusion. The hedgehog concept we selected for the design was to minimize the overall box volume of our heliostat module while maintaining 1 meter squared of reflective surface area. This is important because a more compact module will allow for a smaller, more efficient field and a visual representation of the box volume concept can be seen on the side of the slide. So you have an idea of what we mean by boxed volume.
So looking at our product overview, if you look at this photo that we have here to the left, you can see that we have a 6-foot male figure next to our Lagarto ray, one of the modules of the Lagarto ray. And this gives us good scale so you can understand how big the Lagarto ray would actually be in the field and how it would look in real life. So this is a very helpful visual here. And our Lagarto ray consists of 2 motor systems. It's a 2-motor system, I'm sorry. And it's mounted and placed into the ground using 1 tubular connection. And the size at its maximum, so when these mirrors that you see in the photo are facing up towards the sky, that'd be the maximum size that it could be. It would be 1.3 meters by 0.6 meters by 1 meter. Its weight is going to come in at 24 pounds, so relatively light. And this the Lagarto ray gives you 360 degrees of rotation in both the azimuth axis and the elevation axis. So in the slide, we can see to our left and to our right that we have 2 photos that show all 4 of our subsystems. In the left-hand photo, we see the mirror subsystem, the support structure subsystem, and the actuation subsystem, which also includes the computer at the bottom of that photo. And to the right, this shows what the Lagarto ray would be looking like in real life in the field when it's laid out in its field. And to the bottom left of that right-hand photo, you can see the heliostats laid out as they would be, and then aiming towards the tower, which is in the middle of that photo. So this is our mirror subsystem, and shown to the right is one of the mirrors, and there's 2 per module. So the total reflective area is going to be 1 square meter when you have 2 of them installed, like they normally would be. And we have the our glass mirror, which has an aluminum plated glass, and that is going to be mounted to a polycarbonate frame. And that's going to be mounted using 2-part epoxy and then 2 lips that are located at the top and bottom of the polycarbonate frame, hold the mirror in place as well as a secondary in case that 2-part epoxy was to fail. And then we have 2 U-bolts, which are going to mount the 2 together with 4 nuts and 4 washers. And this will mount the mirrors to the actuation subsystem. The total reflecting power that you get out of each mirror would be 795.6 watts. And both mirrors are going to be positioned low to the ground to reduce the wind forces at play when in use.
So we did some calculations, making sure the specifications of the mirror meets the customer need. We calculated reflectivity for a single mirror. We used the radiosity equation from heat transfer with variables G, A, and mu, where G is the direct radiant solar energy from the sun, which is 850 watts per meter square. In this case, it is obtained through a Nevada power station website, just in case. And A is the total collection area of the mirror. In this case, the area is 1 meter square, and mu is the mirror's reflective efficiency. It turned out that the reflective power is approximately 795.6 watts or approximately 800 watts. Another calculation we did for the mirror was weight. So to calculate the weight of the mirror, we used the density of glass, the total volume of the mirror, with the mirror thickness of 1 millimeters. The weight turned out to be approximately 26 Newton. Next slide. From the reflective power calculation, we see that both mirrors sum up to 1 meter square in reflective area. The total cost of the mirror assembly, including the mirror, the U bracket, and supporting frame, is about $10.50. A mirror design also utilized 2 mirrors per module. The mirror subsystem accommodates 1 meter reflective surface area. This ensures a high ratio of reflective area to ground to the support structure area. And because the mirror does not have any moving parts, the mechanical support of the mirror and the epoxy ensure that with regular cleaning, the mirror subsystem will last at least 20 years. So to sum it up, our mirror design helps satisfy 4 customer needs. The total collection area is less than or equal to 1 meter square. The design utilized 2 mirrors per module. The cost is less than 100 per meter square, and it lasts more than 20 years, satisfying the 4 critical customer needs.
The support structure is comprised of a pile driven into the ground. The structure accomplishes a ratio of ground coverage area to reflective area that is less than 2. And additionally, it provides, its positioning close to the ground prevents shading and reduces wind forces. There are 2 pictures on this slide. One of them, you can see the ground included in the image. And then the second image, you can see that the ground is hidden. So you have an idea of how long this driven pile is and what portion of it is below ground. One of the analyses we conducted for the support structure was a bending FEA under wind loads. The calculation considered 40 meter per second winds, which is approximately 90 miles per hour. That's considered a maximum for the geographical location. Using the conservation of momentum equation, the force on the mirrors was determined to be 1 kilonewton. This results in a maximum stress of 246 megapascals in the support structure, which is less than the yield stress of the material of 310 megapascals.
In our preliminary design report for this project, to finalize the material of our support structure, we constructed an Ashby plot comparing the cost per unit volume to strength. The outer and inner diameter of the pedestal could be determined before deciding on a material because McMaster Carr, our supplier of choice for this part, offers tubing of various metals with these dimensions. Then we determined the total weight that would be imposed on the pedestal by adding up the weights of the entire actuation and mirror subsystems. With these values and implementing the relationship between stress, applied force, and cross-sectional area, we determined the theoretical stress on the shaft to be 0.188 megapascals. This value offered us various material options, including aluminum alloys, stainless steel alloys, zinc alloys, nickel alloys, and lastly, titanium alloys. We eliminated zinc, nickel, and titanium due to a lack of commonality in off-the-shelf parts. Then we finally opted for steel due to its high resistance to corrosion and high stiffness in comparison to aluminum. Further, by opting for steel and its high strength, the support pedestal would reliably withstand high wind loads. Our support structure subsystem fulfills various customer needs. In our opinion, the most pivotal of those are number 5 and number 7. Because the support structure is only 1.5 feet tall after it is driven into the ground, it allows the mirror subsystem to be positioned low to the ground, thereby minimizing shading effects. Further, because our entire support structure subsystem is off the shelf and does not require any manufacturing, the cost of the subsystem's material, manufacturing, and assembly equals $10.46.
For the actuation, we decided a two-motor system, the azimuth and elevation axes, which are individually actuated. We decided to use 19 RPM 12-volt DC gear motors for both elevation and azimuth, and the lifetime of the motors are over 20 years. The azimuth motor uses metal worm gears, and the elevation motor uses nylon spur gears. This allows for a 360-degree rotation of the mirrors. And the motors and gears are sealed in stainless steel boxes, as you can see in the images on the right. And the images on the right do not show the lid, so you can see the motors and the gears. The computer uses a Raspberry Pi with a motor HAT device by Adafruit, which allows the control of 16 motors or 8 modules. The computer box is separate from the module on the ground to prevent from overheating due to more shading from the modules, to control more than one module, and is easier to access for maintenance. The box is polycarbonate to allow for efficient heat transfer to prevent the computer from overheating, and is weather resistant. Here you can see the two exploded views of the two motor systems. On the left is the azimuth axis view, which is secured below the elevation box on the support structure. A 12 DC motor in steel sheet metal box, which is connected to the metal worm that rotates the worm gear. Then the worm gear is supported by the bronze bearing in the azimuth box, which is rotated by the actuation bearing that is mounted by a bolt to secure it in place. The circular X-ring is assembled in between the shaft and the box as a top sealant for the hole, which is also sealed with the gasket, making the whole azimuth actuation sealed from the outside contaminants. The image on the right shows the exploded view of the elevation motor, which rotates the mirrors on a shaft up and down. A sheet metal box holds the shaft that supports the mirrors and the motor that rotates the shaft with two nylon spur gears. The spur gears are held in place with the retaining rings and bronze bushings, which are utilized to support the shaft and allow rotation without friction against the sheet metal box. And the overall system is then sealed with a gasket, making the entire actuation subsystem water resistant and weatherproof. In order to get an idea of the azimuth actuation motor torque required to withstand high wind loads in Las Vegas, the worst case scenario where a full wind load is acting on one mirror. From research, the highest gust of wind recorded in this location was 84 miles per hour. A torque calculation was done by taking the center of the beam to the center of a mirror as a lever arm with length L, as you can see in the image to the right, which resulted in 182.5 Newton meters. Any motor over 182.5 Newton meters would be substantial enough to turn against that wind load. We selected a 24-tooth worm gear reduction for the required torque. Therefore, you can see it resulted in a max torque of 453 Newton meters, which is much larger than the required torque. And then you can see at the maximum required torque, the motor speed geared down goes from 11.4 RPM to 0.475 RPM, which meets our needs for rotation needed for the heliostat mirrors under max wind loads.
For the elevation axis, the worst case scenario for the torque is when the mirrors are completely perpendicular to the ground. This is when the lever arm between the center of the mirror assembly and the center of the shaft is at its longest, as seen in the diagram on the right. This results in a required torque of 1.07 Newton meters to start the rotation upwards, and that torque will go down as the mirror goes up. Although gearing was not necessary for the torque requirements, gearing was necessary for power transfer from the motor to the mirror shaft, as it's not directly linked to the shaft. The benefits include reducing the speed and increasing the torque, and it shows that the motors have enough torque to turn these mirrors in the normal operating conditions. We also wanted to make sure that the size of the shaft was chosen appropriately for the maximum wind load that these mirrors can see, which, as mentioned multiple times before, was at 90 miles per hour. The maximum bending moment, modeling it as 2-point modes where the U-bolts connect to the shaft, is 145 Newton meters, which results in a maximum bending stress of 384 megapascals, where the shaft is supported by the bronze bearings at the elevation box, which offers a factor safety 1.08 compared to the yield strength of the 4140 steel selected for the mirror shaft. We also were interested in seeing what the cyclic load could do to the shaft, and the average wind speed in Las Vegas from our wind data is 5 meters per second, and we use that as our load to see what happened in the cyclic loading, which is a force of 8.15 newtons on each mirror. As you can see, the bending stress caused by this is very low compared to the estimated endurance limit for infinite life of the 4140 steel at 207.5 megapascals, which means we didn't need to look at Marin factors as there is a lot of room between the stress caused by the cyclic loading and the endurance limit, which means the shaft has a life of over 20 years when facing the average wind speeds in Las Vegas. Although very highly dependent on the control system used for the motors, the worm gears and gear systems used, along with the low speed motor selected, allow the user to reduce the tracking errors when controlling the positioning of the heliostats. The rotation axes are capable of any degree of rotation, allowing you to effectively track the sun throughout the day, wherever it may be or whatever time of year it is. Although we do not have an onboard computer, we selected to make it offboard as it offers the same functionality as an onboard computer, but allows you to lower costs in terms of being able to control multiple heliostats at the same time with one computer. Also, all the boxes are sealed to make sure that you can clean it quickly without having to worry about damaging sensitive electronics. And materials were selected so that the system could last over 20 years.
So for our field layout, a semicircular design was chosen. We found it was best to balance out the overall efficiency as well as the blocking from the tower, the blocking from the other modules, as well as the overall compactness. In our field, there are a total of 14 rows with 3 meters of clearance. When we were researching, we found that the average commercial cleaning vehicle is roughly 2 to 2.5 meters in width. So we went ahead and did 3 meters for added maneuverability. On the bottom left, you can see our semicircular design with semicircles extending outwards with a 3-meter gap in between. And the figures on the right show renderings of our Lagarto array in that field layout. So using the desired thermal output of 1 megawatt, as well as the 850 watts per meter squared of solar irradiance that we got from historical solar data in the area, as well as the optical efficiency of 0.713, we found that the needed heliostat area had to be 1,650.03 meters squared. Since our module maps 1-to-1 with 1 meter squared of reflective surface area per module, we needed over 1,651 modules. When we went through and filled out all the rows, when we filled out our last row, we got a total of 1,768 modules. The table on the right shows the different rows with the different number of modules. And as you can see, they're spaced out 3 meters from each other. And the number of modules increases because the arc length of the semicircle gets larger and larger as you extend further from the central tower. So we wanted to calculate the solar concentration ratio. So we knew that we needed at least 1,000 suns to meet the customer need, and we had the area of the heliostats. So by dividing 1,768 meters squared of reflective surface area by the 1,000 suns times the 0.713 optical efficiency, we got that it would be 1.26 meters squared for the area of the receiver. And when we did the calculation of the diameter of that circle, it would be 1.27 meters, but we rounded down so that we would have more than 1,000 suns for the field. And when we went through and did that calculation, we got 1,078.4 suns, which meets the customer need of at least 1,000 suns per field. So here are some calculations assuming a half degree of tracking error. As mentioned before in the previous slide, our diameter of the aperture is 1.22 meters. So that means the radius is 0.61 meters. And when we did the calculations for the elevation and azimuth axis, it meant that the difference between the total height or width in the azimuth axis could not exceed 0.61 meters. We didn't have a problem with the azimuth axis, but the elevation axis for the last 4 rows, the difference did exceed the 0.61 meters. So it meant the last 4 rows would partially miss the aperture. And I say partially because they're slightly off of the aperture, but due to light dispersion, it is likely that there will be light that hits the aperture. So we went ahead and did the overall tracking loss of the field with those 4 last rows added up, as you can see by that equation. And when you add it all up and divide by the total number of modules, you get that the loss is 38.1%. But again, I want to stress that this 38.1% does not mean that these rows will completely be missing. It'll just mean that they're not as efficient as the first 10 rows of the field. So these are some artist renderings of the field. We use graphic design to illustrate a 30-meter tall tower, as well as a couple of rows on the left-hand side. And on the right-hand side, we have a front view of just the first row. Again, there are more than 5 modules, but just to give you guys an idea of what the tower and what the modules of the Lagarto array would look like in the field. So as seen by the previous slides, we did a lot of calculations to ensure that the customer needs are met. Specifically, I wanted to highlight a few of them. Need 3 was met. So we found that the tracking error was 38.1%, which again, it's not all loss, but it's not as efficient. So for need 6, our modules can direct sunlight up to a 100-meter tall tower. But for our calculations, we used a 30-meter tall tower, but we did the calculations. And if we were to do an 100-meter tall tower, the first row, the radius of the inner row would have to be spaced out a lot further. For need 9, that kind of relates to the mirrors, but most of our modules volume is reflective surface area. So we do have a small total area relative to the reflective area. For 14, we did account for the reflected light dispersion. Need 17, as I mentioned earlier, there is 3 meters between rows. So a commercial cleaning vehicle can fit with adequate room on both sides to maneuver through. And all of our calculations were done on assuming a completely flat plot of land for customer need 18.
Here's the overall cost breakdown for the heliostat design. As you can see, we broke the cost down as the prototype cost when individually purchasing parts and the bulk purchase for 1,000 modules. The cost was broken down as off-the-shelf parts, raw materials, manufacturing labor costs, assembly labor costs, and energy consumption to manufacture. The prototype purchase resulted in an overall cost of $274.62 when individually buying parts with a small quantity. For the bulk purchase of parts and materials, the overall cost reduced to $149.42, saving over $125. When solely taking into consideration the bill of materials, the prototype cost was $111.70, and the bulk cost was $98.90. Therefore, the module design meets the customer needs of less than $100 per module for the parts.
So in summary, Lagarto array should be chosen for prototyping in EML4502 due to its minimal volume, 360 degrees of rotation, repairability, and durability, including the ability to withstand high wind speeds up to 90 miles per hour and resistance to desert elements with strong support structure and reinforced mirror backing.
In conclusion, leading its competitors in cost, size, and durability, the Lagarto array is the most revolutionary heliostat of its time. It is sure to provide the optimal solution to your industrial solar processing needs. And we would like to thank everyone that made this project possible, including the UF Renewable Energy Conversion Laboratory, Dr. Sheffy, Dr. Greenslet, Dr. Tradeham, Dr. Traum, our professor, our TA DG, Northrop Grumman, Cummins, and Carrier for sponsoring this project and this class. We'd like to thank you all you guys for your support with letting us take on this project.
Are there any questions?
All right. Thanks for the presentation. That was a nice acknowledgement. Thanks. I'm looking at the time. We've got 20 minutes, 19 minutes left. So if there are questions from the panel, we've got about 20 minutes to discuss.
I got one.
Okay, you're on.
This is Tom Singer from Northrop Grumman. You guys had a slide where you showed what appeared to be a finite element model of a post in the ground. Is that correct?
Yes, we have a driven pile. Is this the slide you're referencing?
Yeah. Like a slide or two after that, you did an analysis of that post.
The
Oh,
FEA model.
FEA?
Yeah. Please don't ever do that. It's a cantilevered beam. It's a hand calc. You guys did I forget what it was you were analyzing a little later on, where you had shear moment diagrams, which is exactly what you should do for this type of structure. Doing an FEA makes it look like you don't know what you're doing. In practice, people do this, and it gives nobody any confidence that they have the knowledge to do a good structural analysis, because this is it's swatting a fly with an atom bomb, right? It's not the tool to use for this. So that said, I did appreciate seeing the shear moment diagrams a little later on in the presentation, and so good job on that one. Let's see, what's holding the positioning of your mirrors? Are you relying on the motor to do that?
So the positioning, so if the axes were directly driven by the motor, that would be true. The motor shaft would be holding the positions. However, there is a worm gear for the azimuth axis and also a spur gear for the elevation axis. Along with that, the motor itself is a gear motor that is very, very geared down. And so the motor itself is not doing as much to hold the positions.
Okay, so you're relying, I guess, ultimately on just not being able to backdrive the motor through that reduction ratio?
Yeah.
Is that going to be sufficient to maintain an angular tolerance when you consider, I guess, maybe potential backlash in that system and overall structural rigidity? Are you going to be able to maintain your aiming tolerance?
So that needs further analysis as to whether the backlash would be enough to take it off target. With our tracking calculations, we used 0.5 degrees, as was suggested by the customer for doing that analysis. But we need to do more work in terms of figuring out the exact angular tolerances when using these systems.
Okay, I would suggest your customer can say, we think you need to hold 5 degrees of positioning, but they don't know or I'm sorry, half a degree of positioning, but they don't know the compliance of your structure. So if it's moving in, on a windy day and it's swaying back and forth and is maybe exceeding that half degree, that may impact the suitability of the system. So that's something to consider. When you were doing the analysis of the load on the mirrors in the horizontal rotation axis versus vertical rotation axis, it looked like you made very different assumptions about what your loading would be. I think for the horizontal rotation load, I think you said, well, let's assume like a maximum wind speed on a single mirror. And then when you did the vertical rotation load, I think it looked like you were just considering the weight of the mirror itself hanging down, slightly off the center line of that axis. Are you concerned about any sort of non-uniform wind loading impacting that?
Yeah, so you're correct about the way we did the analysis. The azimuth axis was the one where the wind load was acting on one mirror. That was chosen as a hypothetical situation in terms of like what's the maximum unbalanced loading that the two mirrors could that you could see under the max wind speeds that we found in Las Vegas. And so this was just to show that even in this hypothetical worst case scenario, it would never be this imbalance in real life, as both you'd have to probably remove the second mirror for this to happen.
Yeah, I'd agree. That's a fairly conservative assumption.
Yeah, the gear reduction is enough to be able to drive through that applied torque by the wind. I didn't have that. That was also done because if you do like a completely balanced loading, mostly what you're fighting against is the inertia of the system in that axis, and also any friction between any of the interfacing objects.
Yeah, this analysis I'm sort of philosophically okay with. I think it's very conservative, but it's not problematic, I don't think. But when you were looking at rotation on the other axis, that's actually where it seems like you'd be more likely to have an unbalanced loading, as you'd have wind sort of going past two of these in a row. Most of the bottom of the mirror is going to be shielded from the wind by the module in front of it, where the top of it is probably going to see a significantly higher amount of wind loading at the top of the mirror. So that's where I think maybe there was an oversight in the loads that were being applied.
I see. I understand. Thank you.
And I think somewhere near here you were doing the structural analysis, and that's where I remember seeing shear moment diagrams. And I remember seeing somewhere where you said you have a 1.08 factor of safety.
Yes.
Is that sufficient? Because that's much lower than even an unmanned rocket, which you'd be severely weight constrained, and you'd be buying structural robustness with a whole lot of paperwork and analysis of materials. And even there, the very, very smallest factor of safety that I've seen acceptable is like 1.1. Something that's mounted to the ground, factor of safety of 2 or 3 might be more appropriate.
Yeah, I understand. So this analysis is done with the 90-mile-per-hour winds, which is already a factor of safety over what we found is the max wind speed of 84 miles per hour. And also, most likely, if you're facing continuous loads at 90 miles per hour, you're probably in some kind of windstorm. And in that case, you're not really going to be focusing on collecting energy. And so, to increase the lifetime of heliostat, you probably put them into a safety mode where you put the mirrors completely horizontal, and you don't have the wind load completely hitting the mirror like a sail. So all those conditions, if in the worst case scenario where you left the mirrors up and then the gust hit it, that's at 90 miles per hour. I feel like there's a lot of factors of safety already built into the wind speed to go over with that 1.08 as well.
Yeah, wind loading tends to be a probabilistic kind of thing, right? So you can estimate, here's my my 99.9% of the time, this is the highest wind load I'll see over the life of this mirror, and say, I need to carry a factor of safety of 2 above that. And if you say, okay, well, we know that we can reliably predict when our winds are going to be above, 50 miles an hour, and we'll put our mirror into a safe mode, then you can use that as, some 50 mile an hour wind loading as your like design condition and put a factor of safety on that. So that's what I would recommend doing. And while we're looking at the fatigue analysis here, you're showing a 5 meter per second average wind speed, and saying, okay, the load that's producing on the shaft is going to be well under your fatigue threshold. And so I can appreciate that, you're looking at a steel shaft and thinking about threshold stresses. But I'll say that your fatigue load is not going to be just an average wind speed, right? You're going to have higher events, and the forces and stresses are going to go with the square of wind speed. So they're going to get significantly higher fairly quickly. So I would just encourage you to consider what those wind speeds would be, and really it's as much that as like cyclic loading, right? So as the wind's blowing over these things, you're going to get vortices that are shedding off that are going to create that sort of cyclic loading. It's not just wind on, wind off that creates that. So you can go back and look at for example, Tacoma Narrows Bridge, where you see things like a steady wind creates those turbulent effects that create cyclic loading. So something to consider there.
Okay, thank you.
Yep.
Okay, still about 9 minutes left. So other questions from the panel?
Hi, this is Elise from Cummins. Great job on your communication, and I like how you thought about weather resistance on your gearboxes, and all your calculations were great. And I like that you considered the worst case conditions. Going back to your supports on the mirror, you're just using those 2 U-bolts, right? So could those slip and loosen over time? And also in the other direction, is there deflection on the mirror? Like at the maximum conditions, did you calculate that?
Yeah, so the U-bolts, if properly pre-tensioned, the chance of it, if properly torqued down, I think it would be really hard for it to slip. The chance is still there, but the rod is the mirror shaft is stock and not machined in any way as well. But there could be some extra safety features, as in increasing the roughness in the area to increase the friction. That could be done, or a flat machined in to ensure that those U-bolts wouldn't slip down, and then you have an angle difference between each mirror.
Yeah, those are good points. Yeah. Also, did you look at the deflection at the ends of the mirror?
So the deflection so we modeled that as a distributed load of 250 newtons over a half of the mirror going height-wise from the support shaft in the middle. And the max deflection is about 3.4 millimeters. Max deflection at the end, under the 90 mile per hour wind load, which is the 500 newtons over the entire mirror.
Can the mirror withstand that?
Alex, do you have an answer for that? Because I don't think I'm the best person to answer that question.
I think, did you calculate it, Matthew? Or...
I calculated the deflection. She asked if the mirror could take that deflection of 3.4 millimeters.
Yes.
Oh. Did I just freeze?
for our final report.
Okay, thanks.
So I've got a couple of questions. So you said earlier on that you were using a low carbon steel. So usually low carbon steels have very poor corrosion performance. Did you do any assessment of the life of that particular steel?
So for the support structure, we conducted the force analysis for the wind and also fatigue analysis, but not any corrosion analysis for that support structure. Considering environmental conditions in Las Vegas, we did not do that calculation specifically.
Okay, and then you talk about your heliostat arrangement is semicircular, correct?
That's correct.
So what is the advantage of having 360-degree rotation of the mirrors if you've got just a semicircular field?
So the 360 degrees of rotation was less of a design goal and more of a product of our design.
He was talking more about the heliostat field being 360 around the tower.
Well, so he basically.
He was talking about the actuation rotation.
Yes, yes,
So,
the actuation.
Yeah, in this field layout, you don't necessarily need 360 degrees of rotation in both axes, but by using an azimuth elevation actuation system, basically with normal normal design considerations, it's basically a product of the design.
Yeah,
we intended to. Sorry.
No, you're good. Continue.
We intended to have 360 degrees in one axis and 180 degrees in the other, was our design goal. But then just by designing it without impediments on the rotation, we're able to accomplish the 360 degrees in both axes.
Okay, and then could we go to the cost? All right, so there's been a bit of changes of this since your poster, right? As far as the, so you got here, because the main driver I get from the customer, right, is cost, and you're a little bit over, with about 50% over on the bulk cost per module compared to the goal. And so could you talk a little bit about, you've got bulk cost per module versus prototype cost, the huge savings you got here in the, what were the assumptions on the manufacturing driving it down 152 to 42?
Our main assumptions there were from research of when you're building a prototype, you have to look at instructions, you have to learn how to assemble something, you have to learn how to use the materials and the sizing and the correct dimensions. And then after the manufacturers get more used to the product, the design, the dimensions, what they have to do, maybe they don't have to refer back to images and design instructions as much, then it'll cut down time substantially. So the manufacturing will cut down to at least 1/3 of what it originally was.
Okay, and then my final question I had was, so why 2 heliostats? I know the requirement was 2 to 16. What drove you to the choice of 2?
Well, we originally had a couple designs that had like 16, but we decided that those required a lot of more motors. And because the actuation subsystem is the most expensive subsystem out of the overall design, we found that the higher number of mirrors required more motors, which increased costs substantially. And that would kind of be a trade-off of getting a low quality motor that would have an average lifespan of 5 to 10 years, which would require repair and more maintenance and maybe was harder with less torque. So that's why we decided that it's safer to have 2 mirrors with only 2 motors, because we can get more reliable gears and more reliable motors that have a longer lifespan and cut down costs.
Okay, thank you.
All right.
Thank you.
So I hate to cut it off there, but we've hit our 45-minute mark, and I want to make sure that we don't fall too far behind with the groups coming up later on this afternoon. So let's wrap it up there. Let's thank group number 5 for sharing their design and giving their presentation. Great work, job well done. I appreciate the and we talked about this a couple of times, that the sense of scale, right? I always imagined in my head that these things are quite a bit bigger than they actually are, but actually showing that figure to give a sense of how tiny and compact you guys are able to make this thing, I think was really, really helpful for me, at least, to visualize that it's not this big, massive thing. It's actually this relatively small package. So appreciate that. Okay, so we'll wrap it there. Let me drop into chat the next meeting Zoom link, and we have a couple of minutes. So we're supposed to start there at 12:30. So we'll wrap this up here. We'll take 3 or 4 minutes just to take a quick break, refresh ourselves, and then pop back into this new Zoom meeting link at 12:30.
Thank you, everyone, for coming. We appreciate your feedback.
Yeah, thank you so much.
Yeah, great work.
Thank you.
Thank you.
All right, see everyone in a couple minutes. Thank you.